Hello, I'm Arman Afrasiabi and I'm going to present our work entitled as Matching Feature Sets for Few-Shot Image Classification. In this work, we focus on few-shot image classification where we have an access to the set of base classes with abundant examples, and the task is to obtain a learning model such as a neural network which generalizes well on the novel classes with only few examples. For example, here we have one shot or one example per each of these novel classes in three-way or three-class classification problem. And the task is to predict or find the label of the query which belonging to one of these novel classes. In this context, a popular strategy is to employ a feature extractor which learns to convert an input image X into the single feature vector at the end of the network. In this work, we depart from this established strategy by proposing the idea of matching feature sets. With this, we take inspiration from feature pyramid networks, which has been proposed to concatenate multi-scale feature maps from convolutional backbones. Particularly, we aim at learning a richer feature space that is more discriminative and easier to transfer to the novel domain by allowing the network to focus on different characteristics of the input image. Our novel backbone is called SetFeat extractor, or briefly SetFeat, which extracts set of features. Given a support-labeled example, our SetFeat, which is a neural network backbone, extracts set of features at different stages of the network which specified self-attention modules called mappers. The same process is also applied on the unlabeled query example using the same network noted by a dashed line in the figure. Having covered how SetFeat extracts a set of features for each input instances to process, we now proceed to see how it leverages these set of features for image classification. In this context, we need to compare the feature sets of the query example with the feature sets corresponding to each instances of the support set to infer the class of the query. We now present three proposed distinct set-to-set matching methods or metric. First, we proposed matchSum that aggregates the distance between matching mappers for query and support examples. Second, we proposed min-min, which uses minimum distance across all possible pairs of the elements from the query and support example. And finally, we propose sum-min, which departs from min-min metric by aggregating the sum of the minimum distance between the mappers computed for query and support sets. We evaluate our matching feature sets with different datasets and backbones. This table presents the evaluation of our set-to-set metrics on the mini-ImageNet dataset by comparing our SetFeat with Conv4 in 1-shot and 5-shot. Specifically, our SetFeat4 with sum-min metric results in the accuracy gain of 1.83% over the baseline method in 1-shot. Next table presents the tiered ImageNet evaluation of our SetFeat12 with the proposed metrics. Like mini-ImageNet dataset, our sum-min metric is the best one and results in 1.42% improvement over the baseline in 1-shot. And finally, this table illustrates the fine-grained classification evaluation of our approach with CUB dataset. We also conduct ablations on the proposed method. For example, here you see the visualizing mappers with tsne on the random samples from validation sets for mini-ImageNet, CUB, and tiered ImageNet. Points are color-coded according to the mappers, and as tsne results show, the mappers work independently. In summary, we present the idea of reasoning on the sets and the set-based inference for feature vectors extracted from images. Our paper presents a straightforward way to adapt existing backbones to make them to extract set of features rather than single one and processing them to achieve decisions. We also present extensive experiments and ablations. Please visit our project webpage for more information. Thanks for your attention.